Shane Larson is the Associate Director of CIERA, and he's a Research Associate Professor at Northwestern University in the Department of Physics and Astronomy. He's also an astronomer at the Adler Planetarium. He earned his master's and doctoral degree in physics from Montana State University. His research interests include, big surprise, gravitational waves, as well as data analysis and a variety of other cosmological events like binary star evolution and gravitational dynamics in extraplanetary systems. He has an incredible passion and knack for public communication of relatively challenging physics and astronomy. So with that, I will now turn the microphone over to Shane Larson.
Okay, well, thank you, Jay, for that kind introduction, and thank all of you for being here tonight for this very special celebration of what truly has been a remarkable and momentous event in the history of astronomy. When you become a professional astronomer and astrophysicist, you often imagine that you will live to see really transformative events in astronomy, things that literally change our understanding of the cosmos and the universe. And I have to say, I never expected to not only witness such changes, but to be part of it. And this has been the most exciting thing that has happened certainly in my career these last few months. And it's very gratifying to know that the work done by our students and our postdocs and our faculty here at Northwestern really is so close to the frontier that there's no way we couldn't have been part of this great discovery. And so what we're going to do today is I'm going to spend this first 10 minutes or so chatting with you about the discovery, about what it was. I'm going to tell you the story to kind of get everyone on the same page, give everyone a little bit of vocabulary, and then we'll have our panelists, our three faculty members, come up, and there will be a little moderated discussion and a chance for you to ask questions about the things that you've heard and the things that interest you the most about this event. Okay? Okay, so if I can get my lights off there so we can see the slides. So anytime you open up a magazine or a book or you see a news story about the latest, greatest discovery in astronomy, invariably you will see pictures not unlike the ones on the screen behind me. All of us have grown up in an era where access to beautiful, robust astronomical images like these are easy to access and are so familiar to all of us that virtually no one can look at a slide like this and not see something that they recognize. This is really how astronomy has been done for the last 400 years. We've been using telescopes, which are mechanical extensions of our eyes, to look at things that are so impossibly far away from the Earth that no person in this room or in the foreseeable future will ever be able to go there. When you look at a slide like this, nothing on here is accessible to individual humans, except maybe the moon. But we haven't been to the moon in almost 50 years. Everything that we learn about astronomy and that we think we know about astronomy has been gleaned by measuring signals that come to us from these enormous distances. We gather them up, we look at them, we study them, we ponder them, and eventually we come to some understanding about how the universe works. And for 400 years, we've more or less only been doing that with telescopes. But as it turns out, there are other signals that come to us from the cosmos. And about 100 years ago, Albert Einstein suggested that maybe another way to understand the universe would be to not use light as a probe, but to try and detect the gravity from distant astrophysical systems. As those systems move and evolve in time, they warp and stretch and pucker the space-time around them. That information, that change in the gravitational field, propagates across the universe and eventually washes across the shores of Earth. 100 years after Einstein had that spectacular idea, an idea that he was not certain we would ever be able to make good on, we have built a machine capable of detecting the faint gravity from distant astrophysical systems. We call it LIGO, the Laser Interferometer Gravitational Wave Observatory. There are two of them here in the United States. This one in this slide is outside Hanford, Washington. It has a twin outside Livingston, Louisiana. And on the 17th of August this year, sometime in the early morning, a gravitational wave signal washed across LIGO. Now, this is brand new astronomy, but already we've made 5 gravitational wave detections. So we're a little bit jaded, and we're like, oh yeah, another gravitational wave signal, no problem. Okay? But what makes this discovery so exciting is that 1.7 seconds after LIGO and our companion Virgo in Europe detected that signal, our colleagues who study the sky using a kind of high-energy light called gamma rays, they have a satellite in orbit called Fermi, also detected a signal. And that was truly the momentous event that happened. We have been anticipating for decades the opportunity to study something in the cosmos, both with gravity and light at the same time. And the moment we realized that it had happened, the worldwide astronomical community mobilized in an effort to try and figure out if we could see this thing with light after we detected it in gravitational waves. And indeed, that's what happened. This is what our data looks like. Now, most of you grew up looking at pictures from the Hubble Space Telescope. But when you're a professional astronomer, this is what you stare at every day. And when I see LIGO data that looks like this, and I see that long, sinuous swoop of a signal across there, I get really excited because I know what it is, I know what it means, and I know I'm going to have a lot of work to do for the next few months. Okay? In a similar way, this is what the gamma ray data looks like. The gamma ray folks are just counting gamma rays in their satellite, but when they see this big bump up like this, they get really excited because they know something happened. Okay? And it's the proximity in time, less than 2 seconds, of this signal and this signal that started the story that you're going to hear about tonight. So what was it? What LIGO told us is that the source was a pair of neutron stars orbiting around each other. Neutron stars are the skeletons of dead stars. They are locked together in an orbit still, even after their parent stars died. And they're going around each other about 10 times every second at the moment that LIGO detected them. They're separated by about 400 kilometers. And as they emit these gravitational waves that LIGO was detecting, the orbit shrinks. And as it shrinks, the neutron stars go around each other faster and faster and faster. There's nothing to see except the gravitational waves, but we can tell what's going on. As the neutron stars get close together, they become sensitive to each other's strong gravitational field. It distorts them until they merge and become one object. And in that titanic merger, it creates the first signal in light that we detected here on Earth, that gamma ray burst that Fermi detected. It also throws out a cloud of material from the collision of the stars that expands out. It's very hot, very energetic, it's very dense. As it cools and expands, it forms new elements. It also emits light. And over the course of the next many months, we're still looking at this source today, all of this material, and including the ejected gamma ray jet, the burst, begins to descend in energy. It begins to cool. It emits gamma rays, and then X-rays, and then ultraviolet light, and optical light, and infrared light, and radio waves, all the way down. And still today, 2 weeks later, many months later, sorry, the initial 2 weeks was what we observed, many months later, we are still studying this object. But that's the whole story. There's about 100 seconds of gravitational wave data, and then there's no gravitational wave data. And then there are many months of data in the form of light, but eventually this is going to fade away, and we'll never see it ever again. Okay? So, these neutron stars are exotic objects, and this is why we care about this. They are the skeletons that form when a star explodes and dies. You can also form neutrons, black holes, but neutron stars are far and away more common. Okay, they're about the size of a city, so you can see it hanging over the Chicago skyline there. If you could stand on top of the Willis Tower with a spoon and reach up to that neutron star and scoop up a spoonful of it, the mass of that sugar cube-sized bit of neutron star material would weigh 30 times more than the entire human race. Maybe a little bit more after Thanksgiving dinner. Okay? These are exotic objects. They are things that we absolutely cannot understand by studying them here on Earth in the laboratory. The only way to understand them is through the science of astronomy. And their story and their evolution is intimately tied into our story of where we came from and where everything we see in the world around us came from. So what does the data from these things look like? This is very typical gravitational wave data. Here's the 5 ho-hum sources that we had seen already. They're all black holes. But on the bottom there, you'll see the signal from the neutron star. Now, I'm a gravitational wave astronomer, and I can tell what's going on. I'm really excited about this. And you're like, wow, painful flashbacks to my physics class. Okay? Waves. These are waves, just like waves that you've been exposed to before. And the problem that we have as gravitational wave astronomers is how do we convince you that there's astronomy in that? The truth is there is astronomy in that. What you're looking at from the neutron stars is different than what's there from the black holes we saw before. That's how we know they're neutron stars. But it's still not very exciting for you to stare at them, but they are indeed waves. And just like I can take the light from a telescope and turn it into a picture, I can take the data from a gravitational wave signal and turn it into a sound. Can you hear it? That is the orbit of the 2 neutron stars getting smaller and smaller and smaller, faster and faster and faster, until they collide at 1/3 the speed of light. Okay? That is the data turned into sound in the same way that data from a telescope is turned into a picture. LIGO spent the first day localizing where that thing was on the sky. We figured it was neutron stars, and there should be light because we saw the gamma ray burst. And by the end of that first day, our colleagues with telescopes around the world, and you'll hear a bit of this story after I'm done, had localized which galaxy it was from. This is that galaxy. It's a small, nondescript galaxy in the constellation Hydra called NGC 4993. It's kind of a ball of a galaxy. It's not pretty and disc-shaped like the Milky Way. But right there in the halo, on the outer edge of the galaxy, there's a bright spot that wasn't there before. And that bright spot is the remains, the ejected light and material glowing softly, fading away after the collision of those 2 neutron stars. So we've been staring at that. In the first 2 weeks, about 70 observatories around the world imaged and studied this in great detail. The source went behind the sun, and our friends who do radio astronomy were the only ones who could see it for a long time. And now it's emerging again, and we're back to staring at it with other telescopes as well. Okay, so that's the story. That's what you're going to hear about. You'll hear about the things that we did to discover it, the things that we've done to analyze it and understand it. Okay, and you'll have a chance to ask some questions. I always like to leave you with something to go see on your own. There isn't a lot written about multi-messenger astronomy yet. Okay, but there's a lot written about gravitational waves. So these are 2 fantastic books about LIGO, black holes, and neutron stars and gravitational waves, which you can see. If you'd like to work on gravitational waves with us, this is a citizen science project that we lead out of Northwestern called Gravity Spy. Okay, you can help us look at LIGO data. And then here's a series of blog posts and video links to things we produce at Northwestern and also that LIGO and Virgo maintain. And there's a lot of the multi-messenger gravitational wave plus EM stuff there as well that you can study on your own afterwards. Okay? If you go look at all of that stuff and you're still confused, you know where to find us. Okay? Okay. I'm going to hand it over to our panelists. So I'd like to introduce Shane Larson from the Adler Planetarium. She's the president and CEO, and she'll introduce our panelists. So thank you all for your attention, and we'll have a little bit more of a conversation.